So what do you want to do today? Well, we're going to go over the assignment, I guess, right? Everyone's okay. Question. This is lab 3. We can also go over lab 3, right?
Lab 3 is due next Friday.
Yeah, January 30. We can go through the assignments. Let's do this. Today is Wednesday, right? Okay. And I can spend time in the lab for those who want me to cover problems in lab. I can do that there. I want to remember, people are still kind of getting used to Git, and one of the things you need to remember about that is that for Git to work correctly, it's not even set up here. If I do cd by itself, I'm now in my home directory. pwd print working directory, that's my home directory on the Macintosh. I could log into the labs using SSH, and then I would have a different home directory location. But this is my home directory here. And the clone command, which you really only need to do once, but you might do it several times. You're working from home on your machine at home that you're not, say, connecting to the lab machines from. And then you can clone the repository locally. Of course, to do that, you need to send me your public key for the new machine you're working from. So I don't see that I saved what I did from last time locally here. So I'm going to clone my repository again. Now remember, my name was Sam, I believe. I'm going to change the name of the folder that I clone into, because I already have a folder called 201. So I can't clone on top of an existing folder. So Sam, I don't believe Sam exists. I'll try to clone into that. Oops, I'm sorry, it's a Git clone. So it accepted it. You know, if I tried to clone again, watch. See, it already exists. So some of you are getting that. You're trying to do a clone, but wait. If you omit, see, if I do this, oh, it's 201. I forgot, I didn't put the .git in there, but apparently it's not necessary. But if I try this, it refuses because I have a folder already called 201. So the clone command isn't going to overwrite something that already exists. It'll create a new folder for you. Anyway, I cloned into Sam. I better get out of there. So see, I did cd. Do you see how fast I'm doing this? So I did cd. I go to my home folder, and then I cloned when I was in my, so you have to think about where you are in the file system when you execute commands at the command line. There's something called a working directory, which is, remember, directory means folder. It's your current folder. It's where you are. All the commands that you issue at the command line may operate or may need to know what this current folder is, or they may work differently based on, you know, different working directories. So the git clone command is an example. It's going to create a folder in your current working directory. By default, you could modify that with specifying a new location on the command line. So cd brings me to my home, pwd print working directory, that's where I currently am, and I'm going to go cd into Sam, that's where I cloned. I'll do ls just to see, look around a little bit, that's there, and we have A1 already started. And I'm just going to do that. Now let's take a look at what we've already done here. We've started a folder called A1. So you need to use these commands, the cd, ls, pwd, mkdir. Those are the commands that are listed in the first lab. So the reason we covered them in the first lab, they don't come up, those commands will not appear on any test. But it doesn't mean you can't ignore them. You have to learn them because you need to do them to carry out the tasks in this class. So here's the file answers.txt. So I'm late on this assignment, but let's do this anyway here. Okay. So we did the first two problems. Let's do the other problems. Oh, was this the quiz?
Yeah, those are practice
Oh.
questions.
All right, let's go and change this then. All right, let me look at that. All right, let's just get rid of this. So that was the practice quiz. So we're going to start with 1, then do 2, and then do 3. All right, let's do this. Figure 1. So here is some code. What does it output to the console? Do we have to read the code? We have to analyze the code. How many top-level statements are there?
3.
2. There's a declaration of I, and then there's a while loop. Those are 2 top-level statements. Now, the while loop is a compound statement. It has substatements in it. It has these 2 substatements. You could call it the body of the loop. It also has expressions. I mean, the while statement has this here. I've highlighted that. That's the loop condition, and we call that an expression. It's a part of a statement. It's like substatements are part of a statement. So we have 2 top-level statements. So we're going to do so. By default, what we do is we do one statement after another in order. So the first statement we do is we create an integer I, we set it to 0. And, we could keep track of that. Maybe I'll do that over here. I won't need that much room. I'll do it like this. So we have an integer I, and I is set to 0. I'll just make a note. Now let's do the second statement. So we have a loop. So the second statement says repeat these 2 statements over and over again as long as the loop condition is true. As soon as the loop condition is true, you have completed execution of the second statement. Is the loop condition true coming in? It is. 0 is less than 7. And therefore, we're going to execute those 2 statements. We're going to print, so see out something, and then we're going to increment I. So we're going to eventually hit 7 up here, and then the loop condition becomes false. So what do we print? So there's 2 operations here. This output operator has lower precedence than the multiplication operator. So we do 2 times, we evaluate the expression 2 times I first. And the result of that expression becomes the right-hand operand of this output operator. So 2 times 0, and I is currently 0. We made a note of that here, but it's easy to remember. We initialized it to there. But the first time you do the loop, it's easy to remember what I is. But as we continue and simulate iterations of the loop, we're going to get lost, so maybe we want to keep track of I over here. So we output 0. Oops. All right. So I'll put my answer here. We output a 0. And, we don't output a space. I'm going to put it in there anyway. Because what I'm looking for is that you can read the code. And yeah, if you don't put the space in there because I didn't output a space, then that's good. I mean, it's nice to see that you would do that, but that's not necessary for these kind of problems. All right, so now we increment I. So I becomes 1. And then we do the loop condition. So I is still less than 7. So, you can see that the I will go from 0 to 1 to 2 to 3 to 4. And then when it hits 6, the loop will run. And then it'll hit 7, and then the loop condition is false, and the loop will be considered done at that point. So we increment I, so we've got the loop condition. I is 1, it's less than 7, good. So let's evaluate, let's execute the second statement. 2 times 1 is 2, and we output the 2. And then what do? Then we increment I. I is now 2. Now we evaluate the loop condition to see if we should continue running the loop. And we should, because 2 is less than 7. The loop condition is true. 2 times I is now 4. We're going to output 4. And then I becomes 3. I mean, you can see the pattern, right? So 2 times I, and I is going up 1 at a time. So it's going to be even numbers, you know, like that, right? Well, I went too far, right?
Yeah, because isn't it supposed to be less than 7?
It's got to be less than 7.
So we will stop at 3. I equals 3.
No, I equals 3, because the I then goes to 4. 4 is still less than 7. What's the last value that I takes on?
6.
It's before the loop condition is false. It's 6. So 2 times 6 is 12. So we will print 12. And then when we increment I and I becomes 7, the loop condition will be false. So we will not do this anymore. We will not print 14. So we'll only print 12. Everybody okay with that? Okay. Let's look at the next one, figure 2. Rewrite the code so that it uses a while loop rather than a for loop to accomplish the same output. Oh, so here's the code, right? Write it as a while loop. Well, someone last period gave the answer. It's actually that, right?
It's the same, Professor?
You just copy this down. Is that the same?
Yeah, it's from the same problem.
Yeah, look at that. Look at that. So the answer is that one there. So I'm not going to write it down. How's that? I would accept that. Well, I'm not going to put it on the quiz, okay, because it's too simple. So don't expect that on the quiz. Maybe the final, I'll sneak it in there. All right, do you want me to talk about that? Maybe I should talk about that. Here, look at the equivalence between these two chunks of code. Do you see look at how much more compact the for loop is in this particular case. In many cases, you want to use a while loop. It's a better way to express the logic. But in this particular case, a for loop works better. Well, I don't know if it works better, but it looks more compact. The for loop, here you have some initialization normally related to a variable that's in the loop condition. So in the for loop, that initialization takes place inside of a statement in these parentheses. See these parentheses right here? There are 3 statements in there. See, statements end with semicolon. And we don't put a semicolon after the end of this plus I statement because we have a parenthesis. And that's good enough for the compiler to know that the statement is done. So we have 3 statements, and you can think of lifting this statement out here, this first statement inside the parentheses of the for loop. You lift it out and place it, before any other logic runs. So it's an initialization step. So you can see that. Now the loop condition here is the second statement. Actually, it's in fact not a statement. So I got to take that back. These are not three statements. That's an expression. It's not a statement. Although it could compile as a statement. So maybe it is a statement. Yeah. Semantics, right?
So, Professor, on
Yeah.
figure 2, would that be the proper way of writing it down?
This?
Yes.
You mean the answer for question 2?
Yes.
No, the answer for question 2 is
Same
this
code.
code right here.
Right.
So you would just, if you wrote this down exactly, that would answer question 2. Now, if I gave this code to you and say, write the equivalent of this code in for loop notation, then you would write down this. So these are equivalent. I'll give you one and I'll ask you for the other. Now, this third component of the for loop, what is that? It's a statement that executes at the bottom of the loop after everything else in the loop runs. After the statements in the body of the loop run. So this is like an end of loop operation. And you typically, in a for loop, typically you're just iterating through some sort of known number of steps. And this is a very typical for loop right there. You have an integer, and it takes on values one after another. This question.
So plus plus I, you add one. So when it's I plus plus, is it still an addition of 1, or how does that change things?
The I plus plus has the same effect in this situation. It's still the addition of 1, and it's still done at the bottom of the loop and before the loop condition is evaluated. So you don't have to worry about plus plus I or I plus plus in this situation. It doesn't make any difference. Yeah.
Can you give an example of where it does affect?
Where it does make a difference? I think we have one coming up. Right there. Okay, we're going to get to it. It has, see here, the plus plus I occurs within a larger, it's a component of a larger statement. See that? So the whole statement, the statement as a whole will run first, and then the increment will happen. Here, the increment happens first, and then the statement that it's included within is evaluated. But here, in this situation, where is it? Here, this plus plus I stands on its own. It's like its own statement right there. It's the end of loop statement. So there's nothing else involved there. So if we made this more complicated so that something else depended on the value of I in that moment, in that statement itself, then it would be significant to consider the difference. But here it's just an increment operation, isolated from everything else. All right, anything else about this? The equivalence of for loops and while loops. Let's look at number 3. How many times does the body of the for loop run in the code in figure 3? I need to make that a little bigger. How's that? How many times does the body of the for loop run in the code in figure 3?
100.
Okay. So I'm not asking you to say what gets printed here. I want to know how many times, this statement runs, not what it prints. So we have a for loop here. And we want to know how many times the for loop runs. All right, before we do that, let's just take note of the first statement. We're declaring a k, setting it to 100.
You said 200?
Oh, 100, 100. Right. This k is set to 100, sorry. And now notice in the rest of the code, k does not change. We don't reassign any other value to k. We don't reassign any other value to k. I think that's right. And but we use k. So wherever we use k, we can just think 100. We don't even have to keep track of k. It's kind of a trick question, actually. It's just, you need to be able to strip away that detail that k doesn't change. You don't need to keep track of k because k never changes. It's just, did I say 200 again? Anyway, it's 100. So let's look at the loop. We declare an I, initialize it to 0. And whatever I is, we're going to compare it to 100. 0 is less than 100, obviously. It's our first time. We're going to run the loop at least once. And then after we run the loop, we'll increment I. Now look inside the loop. We don't modify I. We use I. But we don't modify I. So we know that I is going, it's starting at 0. It goes to 1. It goes to 2. It goes to 3 like that. Up to 99. So when I is 99, does it execute the loop? Yes. Then we're going to increment I. We get to 100. When I is 100, do we execute the body of the loop? No, because 100 is not less than 100. Because this is strict inequality. So that means we execute the loop for I equals 0, 1, 2, all the way up to 99. How many different values are there? 100. We're practicing thinking, counting like a computer, because we're starting our counting at 0. So there's 100.
Because you're counting 0, right, Professor?
Well, it's not as simple as that. It's because of everything I explained.
Right.
Yeah, but you could sort of summarize it in a fuzzy thought and say, well, we're starting counting at 0. That's why it's 100. As opposed to what? As opposed to 99 or 101. The thing is this, off by 1 is a major problem when you're computing. If you're writing programs or analyzing programs or doing system administration, if you're working with computers, there's always the danger of being off by 1. It's called the off by 1 problem. It's everywhere. So when you're doing these kind of problems in particular, you've got to test the bounds there. If you come up with a number and say, well, 99, that's my, or 100 in this case. Well, am I off by 1? Should it be 99 or should it be 101? Because I didn't think of the inequality correctly. And so I didn't consider it, so I'm off by 1. So it's very typical to be off by 1. So that question there is an off by 1 question. So it's a good question. And that's a question you need to ask yourself when you work on these problems. And of course, in a situation where there's something at stake, like a quiz, or if you're spending time writing a program, you don't want to have to debug it by being off by 1. All right, so any other questions on this? When the code of figure 4 runs, what does it output to the console? All right, so this is an output problem. How many numbers is this code going to print out at the most? How many do you think it could print out at the most? How many different numbers could it print? No, how many things is it going to print? It should be quick. You want to find this one, right? It's going to print one thing. It's not printing inside the loop, right? And do you see how I'm using indentation here to show that this statement right here, I equals 3, that is in the loop. And The computer doesn't need the indent. The computer needs the braces, by the way. Well, you could leave it out, but I don't want to get into that detail. It's the human that needs the indent. It's the human that needs to see that space right there. By the way, don't use tabs in your code. Use regular spaces. Well, it's not that tabs push it too far. It's just that how many spaces are in a tab? 4 or 5. Anybody? Any other votes? It depends on your editor. Whatever tool you're using will decide on its own how many spaces to render a tab. And they all use different amounts. Of course, you can configure it. But if you're sharing your code with others, why burden them with the problem of correctly configuring their editor to view your code? So it adds an element of it adds a hindrance to reading your code. So that's why I don't want you to use tabs in this class. I mean, you can, on your own, in a team, you can all agree to use tabs. You don't want to mix tabs with spaces. That's kind of a no-no. Because once again, you have that problem. People are they're gonna view tabs with different number of spaces. Some people are gonna use 4, some will use 8. But the old standard was 8, I think. 8 tabs. Anyway, that's that issue. But we need this indent just visually to see that it's in the body. And look at this line here. This is not indented relative to the while loop. It's at the same level. You see, so there's 3 statements here at this top level. And there's 1 substatement that's embedded within the while loop that's repeated. It depends on the loop condition. So you can just visually inspect that and say, oh, it's going to print 1 thing. I have to figure out what is the 1 number it ends up printing. That's the problem. So let's analyze it. We create an I, set it to 11. And maybe we might not use this, but just in case, I'll just start thinking about keeping track of what I is. So I'm starting my simulation of the computer right now. I'm executing the first line, creating an I, setting it to 11. Now I'm going to execute the second statement. Oh, it's a while loop. Well, so that means I'm going to repeatedly execute substatements within it. All right, let's look at the loop condition. We're going to take our first pass through the while loop. I, which is 11, is less than or equal to 99. The loop condition is true. And so we modify I here. We take the current value of I. Look, we have 2 operations here. Assignment has very low precedence normally. I mean, not normally. It has low precedence in comparison to all the other operators. And addition has higher precedence. So we do the addition first. So I, which is 11, we want to add 3, we get 14, assign that back into I. So I becomes 14. I'm going to write it like this. I'm going to write it like that, just sort of to keep a track of how we got there. And now we did this. Now let's evaluate the loop condition. 14 is less than or equal to 99. That's true. So now we're going to add another 3, right? Now we have 17. 17 is less than or equal to 99. So we're going to keep adding 3s, right? So I'm going to write it if we're going to add, like, some unknown number n times 3. I'll write it like that. So some multiple of 3 we're going to end up adding to 11. So there's different ways that we could approach this. And one way is just to kind of come up with I'm going to do it what I think is the easiest for me. And that is, I'm just going to try to get near the answer. And by the way, what we're looking for is the last value that I takes on. That makes the value that I takes on that makes the loop condition false. Because when I takes on that value, we will then execute this line. So the last value of I is the value of I that we use. Compare that here. Maybe this one. The last value that I takes on, we don't use, because we use I in the body of the loop. But the last value of I is the I that makes the loop condition false. So what we print does not include the last value that I takes on. But this is a different situation. Here, we end up using the value of I that makes the loop condition false. All right, so we need some multiple of 13. We got to have 11 plus some multiple of 3, rather, not 13. We need 11 plus some multiple of 3 that gets us 99 somewhere, right? So let's think about, I'll just do 90, I'll do a mental calculation here. 99 minus 11, that's 88. How many times does 3 go into 88?
29.
Huh?
29 point something.
29 point something. So let's suppose that that the number of iterations that we do 29 iterations of the loop. What's 3 times 29? 60, 80.
87 plus 11.
Thank you. I don't have that. I get to relax up here now. You do the calculations for me. 87 plus 11. I'll do that one. That's 98.
That's close enough.
That's pretty good. So at some point, I becomes 98, right? Now, when I becomes 98, let's suppose we add 3 so that I becomes 98. That means we will compare 98 to 99. 98 is less than or equal to 99. So the loop condition is true. That means we add another 3. So I will then become 101. Is that right? Now we go into the loop condition. The loop condition is now false. I is 101, and we print 101.
Wouldn't it be 101 point something, Professor?
Would it? Well, where do we add anything more? As soon as we hit 101, as soon as I hits 101, the loop condition is false. We're not adding anything more to I. We're just going here and printing it out. We do not execute this because the loop condition is false. Does that make sense? That's the second question you ask like that. That's exactly the question you need to ask. And I'll know that the answer before I even ask the question, but I'm going to ask it anyway, just to check my reasoning. It's like just you want to do a check on your own thinking and reasoning. Any other questions on that one? Yeah.
Why does this one print out 101 as opposed to number 1, which prints out 0, 2, 4, 6? Why doesn't this?
Because the output operation is not within the loop. It comes after the loop. So it is only performed once. And the other example, is it number 1? The output operation is in the loop. It's something that gets repeated. Anything else? Okay. Let's move to the next one. When the code in figure 5 runs, what does it output to the console? All right, so this has to do, what's the theme of this problem? Division, right. There's 2 kinds of division there. You see 2 slashes here, but this is integer division, and this one is floating point division. They are 2 different operations. They're represented by the same symbol. And it's the interpretation of that symbol is based on the context in which it's used. If the operands are both integers, then it's interpreted by the compiler as an integer division. If at least one of the operands has a decimal point in it, then the compiler interprets that slash symbol as floating point division. Integer division, remember, truncates the result of the division, and we discard the remainder. We don't do any rounding. All right, so look at all the operations we have in here. There's division here, there's output, there's division, there's output. And I don't know exactly what sequence the compiler uses for this. But I know that the mathematical operations have higher precedence than the output operators. So these will be done first before the output operator is evaluated. And the output operators are evaluated from right to left. So we do the last one first. And the result of the last one becomes the right-hand side of the output operator in front of it. So we do I'm sorry, it's not right to left. What am I saying? It's all backwards. It's left to right. The evaluation is left to right. Sorry about that. I was thinking. So first we output this half. We divide 1 by 2, and we get what?
0.5.
Huh?
0.5.
0.5. Oh no. That's an integer division. There's no 0.5. 0. Right? Remember, you toss out the remainder. So that's a 0. So we're going to print 0. And then this expression here, Cout, output operator 1/2, that whole expression evaluates to Cout. The 0 gets printed, and you can think of that as a side effect of the output operator. But the output operator itself, once it's evaluated, and the 0 is printed, the expression here is replaced by, and I can't highlight that, by the way. Well, maybe I can. This here, once this expression is evaluated, once it's done, once it's executed, everything that I have highlighted is replaced by Cout. So that's why the Cout that this thing evaluates to becomes the left-hand side of the next output operator. This is called a cascading sequence of operators. The word is cascade. We're cascading the invocations of the output operator. So the next thing we do is we output a comma with a space. And then we output the result of that division, which is what?
0.
0!
0.
I'm going to have a heart attack up here. 0.5, right? I'm sorry, 0.5. Or 0.5, whatever you want. All right, so this is floating point division. That means we keep the remainder. We keep the decimal component of the number.
If it's like decimal, that's when we keep the remainder.
Say it again.
You said if it's decimal, we keep the remainder.
If there is a decimal point in one of the operands or both of them, then we keep the remainder. That's right. Yeah.
Let's say it was 1 divided by 3.00. Would the answer be 0.66 or?
1 divided by 3? It would be 0.333 like that.
Oh, alright.
And what's 1 divided by 3 here without the decimal point? What would that be?
0.
0. Got it. All right. Anything?
I think his question was more, is it going to have a repeating tree, or do you choose the number of places that it keeps? Like if you have
Well,
0, 0,
yeah, no, that's a very good question. We internally, in math, we can represent exactly 1/3, but we can't represent it in decimal notation. Well, we can with a repetition sign on there, right? Internally in the computer, by default, normally we do not represent it precisely. We represent it with an approximation. So internally, we'll have 0.33333 to a certain number, and then it'll stop. But it represents it with binary numbers, not with decimal numbers. So when you convert it back to decimal, you might end up getting 0.3333334 or something that's just a tiny bit off, because we stored the result, we stored the number as an approximation. And so then when we further process on that, we may see inconsistencies like that. We'll just see a little bit of, we call it round off error or truncation error. Huh?
Just using 1, 0 isn't going to have it only go to one significant figure. It's going to round.
That's correct. Internally, has no effect. Using 1 0 versus 2 zeros, like in 3.0 or 3.00, has no effect on how the number is represented internally. There are other ways to affect how the number is represented internally, of course. But in our situation right now, it will not have any effect. Yeah?
I wasn't able to get that program to compile. What?
You can't get this to compile?
Yeah.
And did you copy it like I did right there?
Yes, sir.
I've been having trouble with these PDF documents. They have some of the hidden characters are not what the compiler may expect. And so that may be the source of the problem. Let me see if I have that problem. I'm going to delete all of this. And now what I'm going to do, there's spaces there, not a tab. I'm going to paste in from my clipboard. Looks good, right? Let's see if we have trouble. I hope we have trouble, because then I can talk about what's the reason for the trouble. Look at that. Just as planned. What happened? I'm going to watch this. You know what? It's too hard to read because it scrolls off the top. So I'm going to use this. I'm going to redirect output to a file. I'm just going to have T as the file name. Oh, that didn't work. It's not the text that's being outputted by the compiler is not going to the standard output. This is a redirection operator for the standard output. It's sending this output to what's called the standard error stream. And you can redirect the standard error stream with that symbol right there. When it redirects the standard error stream to the file T. Now you see it's quiet now. That's because it sent everything to T. Oops, sorry, VIT. Look at this. Look at do you see this symbol right there? This caret symbol is marking that location. And it's complaining, warning, treating Unicode character as white space.
What does that mean?
So it's a Unicode character. It's not using the clipboard. When I grabbed the data from the PDF document and copied it into the clipboard, it was grabbing representation of character data that the compiler doesn't like. You know, the Unicode is a methodology of representing nearly all of the characters in all human languages, not all of them, but you know, the major ones. The Unicode is an approach to represent most of the widely used human language characters. And that's so the number of bytes that are used to represent characters has to be larger than the number of bytes needed to represent source code. That's one thing. I don't want to, you know, I'm not an expert on this area, and it gets messy, and I would have to spend time, you know, looking into this issue and preparing to present on this in a more concise way. So what I'm going to tell you at this point, based on what I know, is that it's a problem with the underlying character set. And there are many different kinds of character sets that are used to store character data, and you have to be sort of conscious of that. So in this situation, we have a problem. What do we do? This character here is bad somehow. You know what? Let's look at it in a tool that might be easier to work in. Let me go to Text Wrangler. So here's an editor that's used by a lot of programmers. It's a free tool on the Mac, and it's roughly equivalent to a tool for Windows called Notepad++. And let me go to, where am I? I'm in SAM, right? So we'll go to SAM, and let's look at Lab 2 and this one. And now I can, what is it? Look at this, show invisibles. I'm going to see, oh, look at that. Look at this dot right there. Let me see if I can I increase the font here? Let me, can you see that? Do you see that this dot here, which represents the space? That the size of that dot is bigger than the size of these dots right there. So it's, for some reason, when I produced the PDF document, it used a different character representation of a space than it used here. The compiler didn't complain about the 3 spaces in front of cout. Maybe those are as expected. But the compiler is complaining about the space that appears here. So we take these out. I'm going to just do it manually. You can do it like a replace, right? So we could do something like this. I'll do a replace. Let's do edit. And what is it? Find. Where is find? Text. Look at this, D tab, N tab, just getting off on a tangent of this. So tabs, we talked about tabs already. How can I search and replace? Does anyone see that?
There's a search tab.
Oh, there it is, thank you. So let's do this, replace all. Search, I'll do find. You can see I don't use this. I'm gonna paste in that space, and I'll replace it with a good space. See that? because we can't see the space I pasted in there. Let's see if that works. Replace all. Look at that. The dot, those heavy dots are gone. Now I'll save. And we'll try to compile now. Expected non-ASCII characters are not allowed outside of literals and characters. So there's something here. What is going on there? Is it this? That was it. It didn't like the semi. Do you see it's the same, visually, it's the same semicolon, but it's the underlying byte values that are used to inform the editor that it's a semicolon character. Those are different. So this is the source of the compilation problem you've been having. And for some reason, it's only been in recent quarters that I've been noticing this, and in the past I haven't had this issue. I don't want my changes to go into the repository. How can I bring back the old ex3.cpp file? I use git checkout. Now I have the old version of the file. That's just for your information. But you know, we're running out of time, so we gotta run through this code here. That was a bit of a diversion. Sorry for that, but it was important for some of you. All right, number 6. When figure 6 runs, what does it output to the console? Let's analyze this. So I is set to 2. That's an easy one. And then we allocate a memory for k, and we assign to it the result of this expression. Oh, there's a post increment in there. Is that done before the assignment or after the assignment? Huh? After the assignment. The increment of I, it's a post increment, occurs after the assignment to k. So the multiplication, I times 2, right? That's done with the value that's in I before I is incremented. So I is currently 2, so 2 times 2 is 4. 4 is assigned to k, and then I is incremented. Got it? All right. Now we'll go to the next one. And now this is a pre-increment. That means we're going to do it fast and first. So we're going to increment I. I can ignore all the other operators. That's a pre-increment there. You know, that's got precedence over everything else. So I'm going to increment I. I becomes 4. And then I'm going to, do I multiply by 2 or add k? Multiply by 2, that has higher precedence than addition. So this expression here is I times 2, which is 4 times 2. It's the new value of I that's multiplied by 2. Here, it's the old value of I. Well, it's the non-incremented value of I. Here, it's the incremented value of I that's multiplied by 2. Here, it's the non-incremented value of I, because we're going to do the increment later. Here, we're going to do the increment first. So we did the increment already. I became 4. 4 times 2 is 8. 8 plus k. Well, k is 4. So this expression is 12. So we print 12. Is that tough? You got to practice that, right? And if you don't get it, then you should invent your own problems for yourself. Just do stuff, expressions that are similar to this, and compile it and run it and check the result, because you'll know whether you got it right or not. You don't have to wait for me to look at and tell you yes or no it's right or wrong. Just build a small program to run your experiment, and that way you can practice on these. All right, number 7. Write a program that computes the sum of integers 0 through n, where n is an integer entered by the user. Whoops. So n is a number, and I don't want you to write code that asks the user for n and reads it in. I'm saying that it's already given that happened. Now you just have the n. Now what you need to do is compute the sum of integers 0 through n. So in these problems, you need a variable to keep track of the sum, and we're going to initialize the variable to 0. That's an accumulator. And now the easiest way to do this is to use a for loop, and we'll start at 0, and you know, I didn't say exclusive or inclusive on n. Do we include n or do we not include n? Let's suppose we include n. And I'll try to be more sort of explicit about that. I think when I say 0 through n, that sounds like it includes n, right? So we want to add n into the sum. So it's sum, and I'll just use this abbreviated notation. Whatever I is, I'm going to add it into what the variable sum represents. Nothing else. Okay. That's good enough. Do people understand this plus equals? Another way to write that is this. Okay? This is just a shorter, this is a more compact way of writing what I have in the comment. All right, let's look at 8. Write a C++ program that prints every number between 330 and 550 inclusive. That's a for loop. So let's set our variable. We'll start at 330. And then I is less than or equal to 550 because it's inclusive. We need to include that value of I of 550 in the loop. All right, that's good. Good enough for me right there. And we don't have time to go over this in detail. See, it's a loop. We start the loop counter at 330. We end at 550, but we want to print 550 because I said inclusive here. I'm including the 550. So that's why we need to use this form of the inequality. All right, what about 9? Write a program that prompts the user to enter a number between 3 and 12, inclusive. If the user enters a number inside 313, the problem says good number. Otherwise, this should be the program displays good number. Otherwise, the program displays bad number. So I said prompt the user, and so enter a number between. I'll do this. Enter a number in 312. So we see out that. We see out that, and then we're going to see in what? We're going to see in the number, because we'll need to declare the number. And then we have an if condition. So we want to have some condition here. If it's true, then we're going to print out a good number. Otherwise, we're going to print out bad number. So the whole thing, the main purpose of this exercise is to figure out what the condition is here. So it has to be, the number has to be inside this interval 3 to 12. So it has to be, n must be bigger than or equal to 3, and n has to be less than or equal to 12. You can write it in different ways. There's many different ways to write this condition. Yeah.
Did you put like 3 less than n, less than 12?
Yep, you can do that. I'll show you the other ways you can do this. Wait a minute, it's 106. Let me come back to 9, okay? And then I'll go through the variations. Number 10, the code in figure 10 prints odd when the user enters an odd number and does not print anything when the user enters an even number. All right, so that right now we input a value from the user, and if the value is an odd number, this logic right here, this condition will evaluate to true if I is odd and will print odd number. Rewrite the code so that it prints even number when the user enters an even number. So it's just changing this 1 to a 0. I'm sorry. So it's the same code here, except when we get to this point, if I mod 2 equals 0, well, then we'll see out even number.
It's like the remainder, right? There's just, if it's even, have no remainder. If it's odd, have one remainder.
Did I do this wrong?
No.
Say it again?
I'm just saying. I'm just trying to understand.
Yeah. Say it again?
When it's 0, it's even because 2 fits into an even number and it has 0 remainder.
Exactly.
Now when it's odd, it has 1.
Exactly. That's exactly right. Thank you. That's a correct summary of the reason that this is the solves the problem. Let me go back and just, because this is somewhat important, and that is what about the alternatives in 9? And I'm going to show you an alternative. We could do something like this. We can do if, and I'll do alternative 1, and there's many alternatives. Here is an alternative. If n is less than 3, or n is bigger than 12, then see out bad number. That's the condition. That means n is out of the interval. It's either less than 3, or, that's the symbol here, or it's greater than 12. If either of those conditions are true, it's out of the interval. And you can do other variations. You could do if it's less than or equal to 2, right? It just to show you there's many ways of expressing this. I don't think this is as clear as this one, but that's the way it is. All right, before you go, really quickly, take a look. I'm in here. Watch this. I do git status, and I see what needs to be done. I modified answers.txt. I'm going to add answers.txt, git add answers.txt. Then I do git commit. I need a comment in there. I'll just call it x, whoops, minus mx. And now finally we're going to do git push. Before you do all this, of course, you need to do git pull when you sit down to get Jaren's annotations to your code. That's it. There's a quiz. It's on Monday, right? Quiz on Monday. That's on the schedule. We'll see you Monday.